The most common question I get about people going into space is about why are they weightless? Doesn't the force of gravity still exist in space? And the answer is, of course it does. Without it, the Earth would not orbit the Sun, and the Moon would not orbit the Earth. But yet we see all these pictures of people going into space, and they appear to be drifting around as if they don't weigh anything. The reason for that is their motion. How objects behave in what's called orbital motion. And this lesson is going to attempt to talk a little bit about orbital motion. Then it's going to talk about the devices that enable us to achieve it, and kind of the dual purpose spaceflight and military purpose of this technology. You can model all of this with the little demonstration I'm doing here. You can see I'm kicking two angry birds off the desk. And the red one I'm pushing, the blue one I'm pushing faster. And you can see the difference in the shape of their flight. The red one falls down, follows a parabola. So does the blue one. But the blue one's parabola is wider. You can imagine me throwing these things faster and faster. And the arcs would get wider and wider and wider, until eventually the bird would hit the wall of the classroom, traveling almost parallel to the floor. Newton realized that if you could take an object out of the constraints of the world, if you went up on a very high mountain so there was no walls, and you could throw it very hard, that something really interesting would happen. As these arcs got wider and wider and wider, the Earth would start to curve away from the falling object. Now, these paths are not parabolic because the force of gravity is not always straight down. As you start to go around the Earth, the force of gravity always points inwards. But the idea is kind of the same. The harder you throw it, the wider the arc. And if the Earth starts to curve away from it before it can hit the Earth because you're throwing it faster and faster and faster, at some point you're going to throw it fast enough that the Earth's going to curve away, and it's just going to keep going. Never getting closer to the Earth because it's going so fast that every time it would fall towards the Earth curves away. And you'd go around and hit yourself. That's what's called orbiting. So to make an object orbit, you have to make it go very, very, very fast. Thousands of meters per second. But if you go that fast, it will continue to fall while moving around the Earth. So now that we've established that something in orbit is falling, let's try to link this falling motion to somebody feeling weightless. Easiest way to do that is to think about the free body diagrams for somebody in an elevator that's moving with different accelerations. We've seen this problem before. So as a review, let's just quickly sketch what is going on for a person in various situations. So the one thing I hope we understand is that the actual weight of the person never changes. The Earth is not particularly concerned with your motion. We're going to see what causes the force of gravity later, but it doesn't change based on the fact that you're moving. So the fact that somebody feels different in these situations has nothing to do with gravity. If we're at equilibrium, the normal force must be just enough to cancel out gravity. One of the things I've tried to emphasize now for months is that you don't feel your weight, you feel the normal force. Usually that's kind of the same thing because if you're at equilibrium, they have the same magnitude. But when do you feel heavier? When an elevator accelerates up. And you accelerate up because you've got this normal force accelerating you up. And that's what makes you feel heavier, the fact you're being pushed harder. Conversely, we saw that you feel lighter when an elevator accelerates down because gravity must be bigger with the normal force, so you have a net downward force. So that gets us to this situation here. Obviously kind of traumatic. But if you accelerate more and more down, the normal force is going to drop more and more. It's going to be less and less. What if the elevator's got its cable cut? What are you going to feel? You're not going to have any normal force because you're accelerating down at 9.8, and so is the elevator. It can't push you because it's falling too. So if you feel no normal force here, you feel weightless. So falling equals weightlessness. We are now on the verge of being able to link the big ideas of orbital motion and why somebody feels weightless. If we agree falling equals feeling weightless, then something thrown, like a whiteboard marker, should be weightless if it could feel. And something orbiting should be weightless because it's falling the whole time. So that's the reason people in space feel like they're weightless. They're just like our person in an elevator. They don't feel a normal force. They feel weightless. So how do you feel weightless without going into orbit? It turns out it's easy to simulate. And we'll show some examples of people feeling weightless without going into space on certain aircraft. How does that work? It really depends on whether you understand the answer to this last question. If I throw a baseball, a lot of people might say, hey, the baseball starts falling at this location. But you got to remember, the instant I let it go, this is its force picture. And it has that the whole time. So it's actually falling the instant I let it go. So what it turns out is, if you have a plane follow the same path as the baseball, in other words, a parabola, people inside will feel like they're falling. And you don't even need a special plane to do this. You can do this with a regular commercial aircraft. And NASA nicknamed flights on such the Vomit Comet. And this is how you can practice being weightless before you go into space, so you can experience weightlessness without being an astronaut. You can buy a ticket on one of these planes. And it's how we can film videos, anything from the movie Apollo 13 to certain OK Go videos, to interesting Air Force training videos from the 1950s. Those are all filmed on planes flying in parabolic paths. Simulated weightlessness aside, let's look at what it takes to actually put someone or something into orbit. And let's look at the very first rocket that put a human into space. And that was a Soviet missile carrying the Vostok 1 craft. So this is April 1961, and Yuri Gagarin is perched in a spaceship under this nose cone up here. He's about to become the first human to go into space. This is in Kazakhstan, in the old Soviet Union. The spaceship looked like this. There was a ball-shaped crew compartment, and then all the mechanicals of the spaceship were down here. It was going so fast that, like most spaceships, to re-enter, it had to have protection from the friction it would experience with the Earth's atmosphere, and only the ball-shaped parts survived. This nice big window wasn't part of the ship. This hatch was over there. It's just there so you can see in. But this is the world's first spaceship. It still exists, and it's sitting in a museum outside Moscow. And that's the place where humanity first left the planet. And here's Gagarin sitting in it. So let's look at the American response about a month later. We, too, launched someone into space. And this is Alan Shepard's Freedom 7 capsule on display. This is the first American in space, Alan Shepard. And here's the capsule being recovered after the first flight. And here's a picture of the missile that launched Shepard into space. And you can see he's sitting in Freedom 7, which is on the nose of this missile. Let's take a look at these first flights where human beings became a projectile and experienced weightlessness. Gagarin's flight was mostly around the Earth. He started in Kazakhstan. He orbited around, did almost a complete loop, landing nearby in Russia. A few years back, I was looking at a photo on Wikipedia where someone had plotted that on a Mercator projection map, and I thought I'd do it on my classroom map. So this is the exact same orbit you just saw on a map that's projected flat. And notice it looks like a sine wave. I really like that link between circular motion and periodic motion, which in some classes you may investigate. But math can be beautiful. Let's take a look at the American flights. The United States sent Shepard up a month later. His flight was suborbital. He went up and came back down. It wasn't until the next year where the United States sent John Glenn into space, and he orbited the Earth multiple times before landing. There was a major competition between the two countries, and I think it's important to understand that it didn't just have to do with going into space. There's a reason when we talk about space programs, we often talk about the military aspects of them. I'm using the word missile very carefully here because it's important to understand that these are missiles. And the Freedom 7 missile, the Mercury Redstone missile, is really worth taking a look at because it's literally the same missile as this one, which has a nuclear warhead on top of it. If you want to make someone go so fast they orbit the Earth, you have to put a tremendous force on them. And that's exactly what you have to do if you want to deliver a very heavy nuclear bomb to something across the world. And it's the exact same device that does it. That's what makes things go so fast. And that's why when you hear about countries with a space program that people feel threatened by it, it's because to develop a space program, you also have to develop the kind of missiles that could deliver nuclear bombs. And that's a source of tension in the world as different countries develop that capability. And it's a major thing to understand when you are looking at the history of the space race between the US and the Soviet Union, that as they were developing these technologies to put people into space, they were developing the same technologies to deliver bombs to each other. It actually goes back to the very beginning of our explorations in space. This was the first ever photo in 1946 taken from space. It was taken from an American V-2 rocket. And the fact that it's an American V-2 rocket is a little bit of a strange thing to say, because the V-2 was a feared Nazi weapon from World War II. This is one being launched from Peenemünde during World War II. And they were designed for one thing, which was to destroy London. And they did a pretty terrible job on London. They caused a lot of suffering and killed a lot of people. But they were so powerful that immediately after the war, the United States swooped in and basically seized everything they could from the program, and including the chief designer, Wernher von Braun, who became the chief designer of the American rocket program and helped put Americans into space and later on the moon. And he was the designer of the V-2, which caused so much trouble during the war. So it's important to understand that when you're talking about going into space, you're talking about tremendous forces, and forces that can be used for both good things or bad things. So I hope what you got out of this video is orbiting is indeed a circular motion, and it is because gravity acts as a centripetal force. The link between projectile motion and orbiting is that basically we just throw things faster and faster and faster and make the parabolas wider and wider and wider. and that something that's continually falling will feel weightless, which is why our astronauts on the International Space Station appear not affected by gravity. They absolutely are not weightless, because otherwise what would they be doing in orbit? It's the force of gravity that keeps them there.